We start with the puzzle. In graphs and results tables, the format scientists use to separate quantities and their units is the backslash. Why? We'll give you the answer at the end of the video. Welcome to this Nothing Nerdy video for IB Physics about SI units. Here is the IB syllabus statement. For IB Physics, you're expected to be able to use SI units well. While making a calculation, it isn't necessary to state the units, but they are required for the final answer. In the results table and the graph, you should include the SI unit in the header or on the axis. Here is an IB-style question from paper 1 on the subject of SI units. By the end of this video, you should know how to answer it. Sometimes in IB questions, we're given information we don't actually need, as in this case, and an important skill is to recognise when this happens. There is a redundant word here. Can you see what it is? The solution to the question is near to the end of the video. Every measurement must be stated with a unit. For example, the mass of the moon is 7.3 times 10 to the 22 kilograms. Kilograms is one of the 7 fundamental units from which all others can be constructed. Here is another example of a measurement, the energy of a photon of blue light. It is given in joules, which is a derived unit. The joule is made up of kilograms, meters and seconds, 3 of the fundamental units raised to powers. Most international scientists have agreed to work with the same units in the Système International. There are 7 fundamental units. IB Physics uses 6 of them, which are kilogram, meters, seconds, amperes, moles and Kelvin. The 7th one, candela, isn't required in IB Physics. How do people know whether they are using exactly the same size of units? In the past, it meant having a physical object, such as the official meter or kilogram, against which the unit could be compared. But there is no guarantee that a standard object will remain precisely the same. Over the years, the 7 units have been redefined in terms of physical constants, which are the same everywhere, such as the speed of light in a vacuum, Avogadro's constant, and the charge of the electron. The numerical values of these constants are now defined precisely, and they are used to construct the units. The fundamental units can be built into all derived units. You can use physics formulas to state derived units in terms of fundamentals. For example, to reduce the Newton to its basic units, we use the formula F equals ma and substitute the units for mass and acceleration. Any other formula for force, such as the force to extend a spring, will give the same result. You can test that. If there are constants like pi or 1/2 in a formula, these have no units and should be ignored when working out basic units. Although most quantities must be stated with a unit, some have none. For example, refractive index can be calculated as a ratio of 2 speeds. The units cancel, so when we write it down, it's just a number without units. There are many other units which, although they are not SI, are often used in IB Physics. These include the light year, the kilowatt hour and the electron volt. You should know how to use page 3 of the data booklet to convert them to SI units. Here is the question we asked earlier. First of all, electrical power and power are all measured in watts, so the word electrical isn't needed here. That means that option D is not needed because amperes is included and it's not an electrical quantity, and also option A is not possible because coulombs isn't a fundamental SI unit. So we can write power equals work over time, and then we can write an equivalent formula which is force times distance over time, and then we can reduce the force into mass times acceleration, and that's times distance over time. We don't put equals signs there because they're not necessarily formulae that work, but we can then figure out what the units are: kilograms, meters over second squared, another meters, another divided by seconds, and you can then see by combining those which of those options is the correct answer. Here's the puzzle from earlier. The question was, why is the backslash used? And the answer is that the backslash means that the measurement is divided by the unit, and that leaves only the pure number, and that's what we plot in the graph.